Right. Hello, everyone. I'm Professor Caudill, and we're picking up where we left off with transfer learning. Um, as far as the required reading goes, I did get my copy of Minsky's Perceptrons. This is like the 2017 version, and it's pretty math dense. 2016, 2017. A lot of math, but it reads kind of like a novel. I think I like most about it is it breaks down parallel computing, or if you have like one layer, it really does a good job of specifying how each layer is it's like one feature. So he'll say this is like feature one, this is feature two, feature three, feature four. So this is a very simple. Um, these will look for very simple patterns, and then you have some weight alpha. So these weights are automatically altered with stochastic gradient descent. And then it goes together into a box we call, what is it? He uses the omega symbol. And then that goes into that. From there you get the phi. So there's a lot here. One thing I do like about like the math is a little bit tricky. I don't think the author expects you to really grasp all the math. I think the math is more for him to think. It's kind of like you're watching him think. It's not like tailored for it to be like it's not made to be the math in Minsky's book, Minsky and Popper's book is not made to be like learned. It's more just showcasing their thought process. So one thing I did like is so if you want all of these to fire, he introduces like the ceiling notation but used differently. So you have the sum of all p is greater than 0. So this bracket notation will convert this to a like a boolean. So if this is true, then you can do more interesting things with it. Um, so there's a lot to it, but he really drives home how simple the feature extractions are. So you could test for connectedness. This is within a grid of pixels. You can see which you could have a have a have a feature extractor that looks at patterns where you see how often white dots are connected to or white squares are connected to black squares. So that's called connectedness, concavity, um, parity. What else? which dots are filled. So Minsky is kind of doing like where he's showing like ways to explicitly program the features, but it seems like the trend in the textbook is just let everything be automatic. The only thing we program is changing the examples put and maybe the error rate. Variables. Only thing we program is changing examples. Okay, so yeah, let's get into the book. So last time we were talking about transfer learning. It's understudied. So basically, I don't know if the example with the cats, the one where we actually train. It's like, did we train the model? I think we. I don't know if that's an example. I don't know if the first example in this book was a transfer learning example because I think we actually trained a model on those images. So architecture is a template for a mathematical function. So it doesn't do anything until we provide millions of parameters it contains. So the key to deep learning is to determine how the parameters of a model, how to fit the parameters of a model to get to solve your problem. Okay, so I wonder, because this book is not too old, but it's old enough. So I wonder if it's like nowadays it's so we're talking about the key to deep learning. I wonder if nowadays it is determine how to fit parameters. So I wonder if this also means weights, but maybe not. I think the weights are done automatically, so they must be referencing some different parameters. Determine how to fit parameters of a model via large language model prompt engineering to solve problems. So this is my hypothetical alteration of the textbook. It's like, why should I think? Why should I spend time? It's like a theme here is how much of it can be automated or expedited through like automation. So determining how to fit parameters to models, that's probably going to take a while. You have to really study the model, to study the correlation between parameters and outputs. So I'm wondering if you put a LLM in the pipeline and how much it changes the game. Because I'm not sure this book is. I'm not sure when this book was written. I think it's at least the last 10 years. 2022. Okay. Um, these are videos though. Textbook. 2020. Okay. So this was written in 2020. So taking like 4 years of large language models, that's quite a, I guess it could be relevant. Anyways, in order to fit a model, we have to provide at least one piece of information. How many times if you look at each image? Epochs. Number of epochs. So I think last video we ended with, we're looking at a paper from transfer learning and they had like an image, a 224 pixel by 224 pixel, and then they had like X3. So I'm guessing that was specifying the epochs. That's how many times. Okay, but why is it called not fine-tuned, not fit? Okay, so fine-tuning is adapting a pre-trained model. Transfer learning tag updated for training for different epochs using different tasks for pre-trained. Use one epoch to fit just those parts necessary to get the new random head to work correctly with your dataset. Use the number of epochs requested when calling the method. Fit the entire model. Getting the weights. Okay, so now faster than earlier layers. Pre-train weights. Okay, so what our image recognizer learned. At this stage, we have to we have an image recognizer that's working well. We have no idea what it's doing. So he's challenging the myth that they're black box, not understandable. Machine learning models can be challenging to fully understand, especially when considering how they behave coming across data that's very different than use trained in them. So Matt Zeiler, I think this is one of the papers we downloaded for our required reading, but let me see. Zeiler and Fergus, I think the one I had is this one. Okay, so we should probably download this one. So if you aren't caught up, this is one of the required readings. And then this will now be added to our collection. So Zeiler and Fergus. Okay, so we'll add that. So this is about visualizing the weights. Okay, so not sure what's going on in this picture. So for each layer, image part with a light gray background shows the reconstructed weight pictures. The larger section at the bottom shows shows parts of training images most strongly match each set of weights. So the weights seem to be specifying edges and other simple features and changes in color. These are the basic building blocks the model has learned for computer vision. They have been widely analyzed by neuroscientists and computer vision researchers, and these are very similar to what's in the human eye as well. So it's arguing that the retina uses something similar, like one neuron cell connected to a retina might be tasked with a very specific goal of distinguishing between um, solid and dark, or sharp and fuzzy. So they're looking for corners, repeating lines, circles, simple patterns. So these might be called tokens, maybe. As you can see, this corner here is matching with this. Picture features now identify and match with higher level semantic concepts such as wheels, text, flowers. Layers 4 and 5 can identify higher level concepts. So you can see the patterns are they're going from like simple to more complex. You go from simple arrangement of shapes to actually um, faces of dogs and stuff. When we fine-tune our pre-trained model earlier, we adapted those last layers, focus on flowers, to specialized cats, dogs. Okay, so we have a bunch of examples, images, and it's going through several layers, dot, dot, dot. So we are focusing here. This is the last few layers are what we do to so these last few layers are what we change. We splice out these layers and we put in what we want to specify on. That's what I'm kind of gathering. So image recognizers can do non-image tasks. So sound can be converted to a spectrogram. Time series can be easily converted into an image plotting the time series on a graph. First, this guy created images from a time series from olive oil classifications. So I'm not sure what's going on here exactly. But we have another. It's a little cut off. Another AI student, Yasmin, fraud, working on fraud detection, using data some mouse movements and clicks. Turn these into pictures by drawing an image where the position, speed, and acceleration. Our classification. Okay, I guess we can read this too. So we're gonna take this DOI link, going to Sci-Hub, paste that, and now we have access, and we'll download this, Kalash and others. Okay, so we might as well read that paper as well. It's only 5 pages. Okay, so I see the cleverness in this. It's like if you can draw a pic, if you can try to like represent things as images, even if they weren't originally, you can kind of do cool things, I guess. Um, so for example, yeah, so like say I made a model that, let's say I made like a graph. Let's say like this video gets 20 views in, what is it, 20 views in 3 days, with title T. Okay, so say this, given this, we can convert this into a graph. So this could be views, and this is days. So, and then we have a title. So if this is one image, then is it possible to to use a bunch of examples of graphs like these, and then figure out what video titles, like to predict what video titles are more likely to have a greater velocity of views. That might be one thing we could try. I don't know, just kind of thinking out loud. So deep learning vocabulary. Parameters value in the model that change what task it can do. Updated through training. Fit, update parameters in the model that such predictions. Model using input data match the target labels. Pre-trained model that's already trained. Fine-tuning is updating a pre-trained model for a different task. Training set, training use for fitting the model. So the 7,000 images of cats and dogs was the training set. Overfitting, training the model in such a way that it remembers specific patterns. So that's a bad thing. So convolution neural networks is good for computer vision tasks. So I think that's one that is pretty cool idea, like using computer vision on things that are not obviously images. And what they're doing here is they're making kind of a time series of data, I think. Or not necessarily, but the malware one is very like, I would say that's probably the hardest one to understand. So machine learning is a discipline where we define a program not by writing it entirely by ourselves, but by learning from data. Deep learning is like deep learning is a specialty within machine learning that uses neural networks with multiple layers. So the key is multiple layers. Minsky and Popper in their perceptions book, especially in Rosenblatt, they use single layers. Start with labeled data, that is a set of images that have assigned a label to each image indicating what it represents. Goal is produce a program called a model given a new image to make accurate predicting regarding what the image represents. Every model starts with a choice of architecture. That's like the mathematical architecture, mathematical structure. Process of training or fitting the model is the process of finding a set of weights that specialize that general architecture to work well for a particular kind of data. So for example, with the one where he converts audio to spectrographs, they have to fit it to get the patterns because the the pre-trained model will have a set of patterns like edge detection. It'll look for patterns of color changes. So our job is to change the higher level layers or the weights of the higher level layers. When we train a model, a key concern is to ensure that a model generalizes. So it learns general lessons from our data, which also apply to new items it will encounter so that it can make good predictions on those items. Risk is that if we train our model badly, instead of learning general lessons, it effectively memorizes what it has already seen, and that's bad. So we want to avoid overfitting, divide data into two parts, training set and validation set. Validation is usually like 20% of the so if we have 7,000 images of cats and dogs, we take 20% of that and we set it to the side. And then we use the rest of it as training to change the last 5 layers, but to change the last few layers that look at higher order patterns, I think. All these concepts apply to machine learning in general. Schemes, defining model, training with data. What makes deep learning distinctive is a particular class of architectures based on neural networks. So deep learning uses neural networks. Or convolutional neural networks. Not just for image classification. Let us talk about something that is critically important: autonomous vehicles, localizing objects in a picture. Self-driving car does not know where a pedestrian is, then it doesn't know how to avoid one. Creating a model that can recognize the content of every individual pixel is called segmentation. Here is how we can train a segmentation model with fast AI using the CamVid dataset from this paper. One other area where deep learning has dramatically improved in the last couple of years is natural language processing. Automatically translate one language to another. Here's a code training a model that classify the sentiment of a movie review better than anything that existed in the world just 5 years ago. So uploading movie review data set and yeah, I'm not sure what exactly the 4 is doing. In a Jupyter notebook, the order in which you execute the cell is very important. When you run the first cell, yeah, okay, I know, I think I understand that quite well. Outputs can be deceiving because it includes the last cell. Zero twice will restart the kernel. Okay, that's kind of good to know. Doc learn dot predict. Okay. Doc, it's not defined. Learn is not defined. Okay, so I'm not sure. Maybe it'll be clear later. So I like CSV files. CSV files are just super simple. Tabular model is a model that tries to predict one column of the table based on the information of other columns. Okay, so they're going pretty fast. They're kind of showing like very sparse examples. Um, I prefer doing like one like very focused example, like the cat one. They're just kind of showing like quick examples. I don't think we'll really get much out of running these ourselves. So that's why I'm just kind of skimming through it. Data sets are food for models. So people that create data sets for us to train our models are often underappreciated heroes. Some of the most useful important data sets are those that become important academic baselines, that is, data sets that are widely studied by researchers and use some of the household names. ImageNet. Data sets used. So what is, I'm curious of what these are. Because this is a handwritten database. Okay. Seen that before. What is this one? This is the This is a collection of images. Okay. As you learn data sets throughout this book, think about where they might come from, how they might be curated. Then think about what kinds of interesting data sets you could create for your own projects. In fact, this is how the world's top practitioners do. You don't need the full data set. You can get away with just a small part of it. Gold models make predictions about data, but the model training process is fundamentally dumb. We train a model with all our data, evaluate the same data, can't can't tell how well a model can perform on data it hasn't seen. Without this very valuable piece of information guiding us in training our model, there's a good chance it would become good at making predictions about the data or perform poorly on it. So we have a training set, which our model sees, and the validation set, which is used for evaluation. This lets us test the model, learns lessons, and generalize the new data. Don't want to get good results by cheating. If it makes accurate prediction for data, that should be because it has learned characteristics of that kind of item, not because the model has been shaped by actually having seen that particular item. Splitting off our validation data means our model never sees it in training, so is completely untainted by it. It's not cheating. Be right. Models by training its weight parameters once. Instead, we are likely to explore many versions of models through various modeling choices regarding network architecture, loading rates. Parameters about parameters. We modelers are evaluating the model, looking at predictions. So subsequent versions of the model are indirectly shaped by having seen the validation data and just automatic training process. Just so we hold back the validation training, we must hold back test set data even from ourselves. It cannot be used to improve the model, it can only use to evaluate the model at the very end of our efforts. We define a hierarchy of cuts of our data based on how fully we want to hide it from training and modeling processes. Training data is fully exposed, the validation less exposed, test data is totally hidden. This hierarchy parallels different kinds of modeling and evaluation themselves. With backpropagation. Okay, so I think the takeaway is reducing bias is important to get good models. Doesn't mean we always need a separate test. If you have a little data, you may just have the validation, but generally it's best to use one if at all possible. You ensure that you really understand what test and validation sets are when they're important, then you'll avoid the single biggest source of failures we've seen when organizers decide to use AI. So pull some test data that the vendor never gets to see. Then you check the model on your test data. You decide what level of performance is accurate. Okay, so there's a lot to this. Using judgment in defining test sets. To do a good job of defining a validation set, possibly a test set, you'll sometimes want to do more than just randomly grab a fraction of your data set. So they must be represented by data in the future. One case might be that if you are looking at time series data, for time series, choosing a random subset will be both too easy and not representative. Your data includes the date and your building model in the future. You want to use a continuous section, latest validation set. Training validation sets. This competition organizer ensured that entrants were making predictions for a time period that was in the future. This is a way to fund traders to do back testing. So this video so far, I'm not like the biggest fan of the textbook. I feel like it could just like word things better. I feel like there is like a speed run there exists a speed run path to becoming an expert in deep learning. I feel like the book needs to be aligned closer with that speed running path, and I can sense that it's, I don't know if it's the English or if it's the way they're approaching it, but I feel like there's a more optimal textbook that could be written that just kind of gets right to the heart of it. A choose your own adventure moment. If you would like to learn more about how to use deep learning models in practice, including how to identify and fix errors, create a real working application, avoid your model causing unexpected harm to your organization and society in general, keep reading. If you want to start learning the foundation of how deep learning works under the hood, skip to the MX basics. Um, so I guess we'll just keep going in order. Big hard to know pages and prose, what are the key things? List questions. It's just all these questions are available in the text of the chapter. Just understand it. Answer the questions are on the book's website. You can visit the forums. For more questions. Okay, so do you need these for deep learning? Lots of math? No. Lots of data? No. Lots of expensive computers? No. No. Name 5 areas where deep learning is now the best in the world. Okay. I don't have time to go through the book, so we will use a language model. So image recognition, medical imaging, facial recognition, language translation, text generation, speech recognition, game playing. This is like this piques my interest, I would say. I don't know. Kind of grew up playing games. Um, what is the first device that was based on the principle of artificial neuron? That was a perceptron by Rosenblatt. It uses an array of photovoltaic cells, simulate learning. Okay, so this is way. It seemed pretty accurate. Not going to lie. Based on this book, what are the requirements for parallel distributed processing? Framework for understanding. So this is McClellan and others. Um, we are like we are like 5 or 6 chapters into this. It's the book's open source on Stanford on McClellan's Stanford paper, but basically nodes, units, it's basic elements that simulate neurons, connections or weights or parameters, links between nodes that simulate synaptic connections, just strengths. So information is represented across multiple nodes rather than localized in a single node. So use Perceptron uses Hebbian learning. So if 2 nodes are activated, then the strength increases. So if 1 node okay, so let's say this and this activate simultaneously, then okay, I think maybe I should do it like this. Okay, so if this activates and this activates, then this value, let's say it is synapse, let's say, let's call it an axon of value 1 gets increased. Okay. So remember these layers are simple patterns of different orders of complexity. So if a lower layer and a higher layer are activated, then that connection gets strengthened. So a series of patterns of different complexities will align. So these like sigmoid RELU, these it's kind of like taking a group vote if like a neuron is all firing or not all firing. So you have a partial set of neurons firing. Sigmoid function will take that and convert it to be a value between 0 and 1. So if it's closer to 1, I think it fires. I think. Don't quote me on that. But so parallel processing, it's not. It's from what I've gathered, it's still not precisely. This is not necessarily like correct. Um, if you like the idea of parallel processing, what it really means is like you have separate computers. So like let's say one element of the GPU is going to do this feature extraction, another element is going to do this feature extraction. Or if you have just a lot of money, you put one GPU per layer or per node. The idea is to like distribute the computing per node, not necessarily parallel, because the if you look at parallel in the smallest units of time, nothing can really compute at parallel. Like all the computers in the world right now running are not quote parallel processing. If you had like a million frames per second slow motion camera that you were able to visualize each binary action, it's all serial, but the idea is to split up the computation among nodes. What are the two theoretical misunderstandings that held back the field of neural theoretical? So perceptron. So this is a book I'm reading right now. Single layers are problems, like not being able to capture the XOR. So this is solved with multi-layers. Oh, I think I read like GPUs. I think the modern intro, this mentions like GPUs and big data were like one of the key things. So GPU is a specialized thing for so GPUs are um, okay. How is a GPU different than CPUs? So CPUs are designed with a few powerful cores. GPUs composed of thousands simpler cores. So CPUs are general purpose. GPUs are specialized. Okay. So we're about out of time. So we will pick up on question 7 next time. Thanks for hanging out. It was very wordy episode. So I hope you guys do not mind that. I think even that we made some progress. So I think we will do a lot more hands-on in the near future. So stay tuned and I'll see you next time.